Swayam Prabha. Digital India. Educated India.
In the last lecture, I just started discussing about the stability of the phases. So as you know, phase transformation involves change from one or more than one phases to other phases in a system. So that means under certain experimental conditions, the parent phases were unstable or metastable, and that's why they have undergone changes. So it boils down to the question which needs to be answered is that what are the conditions for stability of the phases for a particular set of experimental conditions, and that is what we have been discussing. So in a nutshell, it asks you a question about equilibrium conditions of the different phases. If the phases are at equilibrium condition under certain experimental conditions, they will not undergo any changes. Only when they are away from equilibrium, the phases will undergo transformations. So equilibrium in thermodynamics means all the three important conditions to be satisfied. First, the system must be in mechanical equilibrium. That means that energies of all the atoms, whether it is a potential or kinetic together, must be at the minimum level. Second is the thermal equilibrium, and as I explained in the last lecture, thermal equilibrium of the phases means that there is no net temperature gradient existing in the phases of the system. And the third conditions to be satisfied is known as chemical equilibrium. That means for the chemical reactions taking place in the system, both forward and the backward reaction rates must be equal. When all these three conditions are satisfied, then only we call the system at thermodynamic equilibrium. Please remember this, because we always consider mechanical equilibrium to be the main or the sole aspect for equilibrium in the very nascent manner. We never consider the thermal and chemical parts are important, but thermodynamic equilibrium means all the three things to be satisfied. Now question is this is all fine in the aspect of theory. How we can put it in terms of mathematical formalism? And that's why we have to get into functions. And if you look at, if you have studied thermodynamics even a small amount of it, you will find in thermodynamics we define a function known as phi energy, and this phi energy tells you the available amount of the energy available, or amount of energy available rather, to do work. So in metallurgical thermodynamics we always consider Gibbs free energy to be the main parameter controlling the stability of the phases, and the way Gibbs free energy is defined is given on the screen. That is, the Gibbs free energy is always marked with a letter called capital G. It is a function of both temperature and pressure. In metallurgical system we always assume pressure to be at 1 atmospheric pressure, so that is why I have written G as a function of temperature, which is equal to H as a function of temperature minus T multiplied by S as a function of temperature. So what are these parameters? H is known as enthalpy of the system. Enthalpy means basically is defined as like this. It is known as, okay, let me write down, this is defined as H equal to E plus PV. Okay, so E is the internal energy of system and P and V are the pressure and the volume of the system. So therefore H is nothing but the total energy of the system in the sense of internal energy plus the pressure and volume term, and internal energy is obviously summation of the kinetic and the potential energy of the atoms. H can be correlated because it's E plus PV is very difficult to measure experimentally. So that is why H is always correlated with a measurable quantity known as Cp, that is the specific heat at constant pressure. And Cp, as per the first law of thermodynamics, is given by del Q by del T at constant pressure, and as constant pressure, if you know, that del Q is nothing but del H del T. How it comes is very simple this way. We know that at first law of thermodynamics tell you del Q is equal to del E plus P d del W. Okay. So remember, this del is basically corresponds to the functions which are not stress functions, and D correspond to the functions which are state functions. This is the way we differentiate them, and this can be written as dE plus PdV. Okay. So therefore, at constant pressure is constant pressure, this is nothing but equal to dH, because if we differentiate the top equation H equal to E plus PV, so del H is del E plus del PV PdV plus VdP. So at constant pressure dP is equal to 0, that means it's equal to dE plus PdV. So that's how we get Cp is equal to del H by del T. So that means del H is nothing but Cp dt. So this can be calculated by knowing the value of Cp integrated over temperatures T1 to T2. In actual sense, we measure H or enthalpy just by knowing the Cp of the system. If you know the Cp of the system very well, we can calculate the enthalpy of the systems very nicely. Now next term is known as enthalpy. The next term is known as the entropy. Before I discuss that, I would like to tell you that we are never interested in calculating in thermodynamics the absolute values of these functionals like H or S or G. We are always interested to know the change, or rather delta values of these functions. So that is why H2 minus H1 is already shown you here, is basically Cp dt integrated over T1 to T2, or you can calculate H2 as a function of H1 plus this integral. So these are the routine formulae you should know to solve the problems in the course. So as a general functions of H as a function of temperature, we always write Ht is equal to H reference plus Cp dt integrated over T reference to any temperature T, where H reference is a reference value that is normally taken as enthalpy at a constant temperature and pressure. Normally we take at 25 degree Celsius temperature and 1 atmospheric pressure. But remember, this H reference has no meaning, because we never will be interested to know absolute value of H. We will be always interested to calculate delta H. So delta H is nothing but at Ht minus H reference. So that means we are always interested to calculate the integral value which is shown in the function, that is this one. So that is what is important when you know when you calculate the free energy functionals. So now entropy is obviously the second term. S is known as entropy of the system, and remember, entropy is always a difficult concept for the students to understand. We will discuss about entropy later, what is the physical meaning of it. First you have to understand what is the mathematical meaning of it. You know, second law of thermodynamics defines the entropy, and we know the second law of thermodynamics tells you that entropy is defined as like this: dL is equal to del Q reversible by temperature. So where the change of entropy ds is given by del Q reversible, this is reversible heat change divided by the temperature T. So that means this this change is defined as a particular temperature T. This is the real definition of entropy, which directly originates from the second law of thermodynamics. So we can simply write down, we know that this del Q reversible is equal to T ds, right. So del Q, we know that Cp is basically equal to del P del Q by del T at constant pressure, that means del Q is equal to Cp dt. So therefore we can write down by connecting these two, del Q and this del Q, the Cp dt is equal to T ds. So how do you get that then? The ds is nothing but Cp by T dt. Remember, ds, entropy, is a state function, that is why you use a d, not del. But Q, heat change, is not a state function, it is a path dependent function, that is why you will use del. So these are the very basic things you should know from thermodynamics. as I said you in the first lecture, you must have some basic idea of thermodynamics. I am not going to go back on each of these things and explain you of these situations. Okay, so finally we can write down this way that entropy is nothing but, entropy change is nothing but integral Cp by T over T1 to T2. Again, we are interested in calculated change, not interested in calculated the absolute value of entropy. And we can always write down the same equations like we have done in case of enthalpy. So finally, G is a function of enthalpy and entropy for a different values of temperature and pressure. When pressure is constant, it is only a function of temperature for pure materials, right. So by knowing Cp, I can calculate enthalpy and entropy of the both these parameters using these simple integrals or simple integrations rather. Once you know that, you can actually do all kinds of stuff, all kinds of mathematics. Let us do that. It is always better to use plots, because plots will give you the direct link between the physical meaning of these functions and the applicability. So let us suppose I am plotting temperature on the x-axis and plotting these functions enthalpy, entropy and free energy. Obviously free energy depends on enthalpy, entropy on the y-axis. So let us suppose Cp, most of the material Cp can be approximated as a function of temperature like A plus Bt. This is until first order approximation. One can actually keep on adding terms, okay. But for simplicity, we will assume Cp is equal to A plus Bt. This is nothing but a straight line. You can see here the slope is B, intercept is equal to A, okay. So now I integrate it the way its functions are shown. So H will be equal to H0 plus At plus half Bt square, okay. I don't want to do the maths. You do yourself in your problems, you will get it known. So this will look like this, that is the red curve. The white curve is basically entropy. Entropy is given as S0 plus A log of T plus Bt, because it is Cp by T. So therefore A log of T will become dt by T is log and integrated over certain temperature. So these are the values of the functions we can easily get. We can actually approximate this way. Now how do I get minus Ts? Minus Ts is nothing but S into T taken minus. So that is what it looks like. The dotted red line, a red curve is shown below. Now what is the G? G is nothing but H minus Ts, because Ts I know, H I know, so therefore I can know G, and G is shown like this: H0 plus A minus H0 T minus half Bt square minus At log of T. So if I plot that, this will look like this. That white line which you see here is what is Gt. So what do you see from this curve? It is basically a curve with a negative slopes. That is obvious, because entropy absolute value is always positive and G is given as H minus Ts. So therefore if I simply take differential of these, the slope of the curve will be equal to minus entropy. So that is why it has a negative slope, and entropy is always positive value, it cannot be negative absolute value of entropy, that is why it has a negative slope. And this is what you should know very well. Now we can see here there is a crossover between minus Ts and the G, that is where H is equal to Ts, because H is equal to Ts means the enthalpy and the entropic parts are equal. That is why it happens. Now I can write down this, because H is equal to 0 here, so G is equal to minus Ts. I am sorry, I said wrongly. So here on this point H, this is nothing but G is equal to minus Ts, because H is considered to be 0 here. You can see here H is 0 here on this point, because this is lying on the temperature axis. So therefore any point lying on this temperature axis for any of these functions value is 0. Okay, so let us examine. So that is what is the G looks like. So therefore what you take away from this message, from this plot, although it looks like very it's done with, the only thing you should take away is this curve G as a function of temperature at a fixed pressure. It looks like this kind for a pure component. Remember, we are not discussing about unpure components, we are discussing only about pure components. Let us look at G of different phases. What we will look at, because we are considering stability. So stability means we have to compare different G values. So these are my two G. The red curve corresponds to G of liquid, and this is G of liquid, you can see here, this is G of solid. Let us consider for the sake of understanding, in a beaker you have a ice as I shown you, and you have water, okay, and both are H2O, this is solid H2O, this is liquid H2O, pure components, no difference, and they are in touching, they are in actually in equilibrium, let us suppose. If they are in equilibrium, and if I plot the G of the solid and liquid, there will be a crossover, as you can see. It will come clear to you why this crossover is present. This is the crossover where G is equal to, G of solid is equal to G of liquid, correct. So at that point, both the phases have same value of phi energy, and as I told you at the beginning of my lecture, the G or the phi energy or Gibbs phi energy value dictates the stability of the phases. That means by comparing the relative positions of the G as a function of temperature at a particular pressure, I can clearly say which phase will be stable, which phase will be unstable. Let us do that now. So at the crossover, both are equal, and that is what is going to happen at 0 degree Celsius temperature and 1 atmospheric pressure, because at 0 degree Celsius temperature, 1 atmospheric pressure, both ice and water are stable or coexist. They will not, there will be no net reactions between ice and the water. They will be at mechanical, thermal and chemical equilibrium, because that is what is the equilibrium melting temperature of ice or freezing temperature of water at 1 atmospheric pressure. So that is why at 1 atmospheric pressure, G of S or G of the ice or G of the water or liquid will cross over, and that crossover tells you they are equal. So that means there is no net difference between the phi energy of these two phases. Now below 0 degree Celsius temperature or 273 Kelvin, Gs is less than GL. That means the phi energy of the solid is lower than the phi energy of the liquid. As you can see here, phi energy of solid is at the they are lying at the below the phi energy of the liquid. So that means below 273 K or 0 degree Celsius, ice is more stable than water. That means if I cool down the water below 0 degree Celsius, water will slowly transform to ice. That is the first phase transformation I have been telling you always. So that is very evident from the G. That is why you always think about Gibbs phi energy. Gibbs, you will come to know about Gibbs, William Gibbs, from many of the internet sources. He was one of the great scientists in the field of thermodynamics and material science, and these functionals puts down the theory in mathematical formalism in such a way you can explain most of the observed phenomenon. Okay, now if I go on the other side, that is above 0 degree Celsius temperature, we know above 0 degree Celsius temperature water is more stable. Ice will melt down to water. How we can explain that? It's very clear from these two relative disposition of these two curves. G of solid is higher than G of liquid. So as the G of solid higher than G of liquid, liquid will be more stable, because the stable phases will always have lower, correct. So this is what you see very clearly on this plot. You do not have to do a rocket science to understand this. It's very simple and very easily understandable in graphical form. That's why we always go for graphical representation of these equations. Mathematically, most of the things looks like little complex, but the moment we plot on a two-dimensional plot as a function of temperature, as a constant pressure, things will very clearly understood. So this same thing I can do it, and that's I mentioned already, the temperature at which both the solid and liquid phi energies are equal are known as the melting or solidification temperature. Here it is written as Tm. Okay, now if you look at the slopes of this curve, as I told you, the slopes of this curve is again and in the last slide only I discussed. I am just showing you in detail so that you understand it very clearly. This is not the entropy of the solid is equal to minus Gs delta G of the G. This is functional actually, the first derivative of G as a function of temperature. This is at 1 atmospheric pressure, therefore there is no need of writing P as a subscript because pressure is constant. Similarly, entropy of the liquid is equal to this. So rather I can write down GST at constant pressure is nothing but minus S, and because S is always positive, this slope is negative. because you have minus sign. And similarly, G of liquid divided by, or the first derivative of G of liquid at some temperature is equal to minus, or this is SS, sorry, this is SL. Okay. Entropy of anything, solid, liquid, gas, doesn't matter, absolute value is always positive. Only third law of thermodynamics tells you entropy of a pure crystalline solid at absolute 0 degree Celsius temperature is 0. At above the absolute 0 temperature, any system will have a positive value of entropy. Okay, now can I do this thing in terms of delta, that is the change, because I have been mentioning you that this change is what is we are interested, change of this relative change of these functions, not the absolute values. So let us do that. Okay, if I do that, so let us consider this in terms of delta G. Okay, for a simple system, let us plot again everything. G I have already written there, delta G looks like this. Okay, you please do not ask me to do the maths, you can do yourself. Now delta G is nothing but GL minus GS, that is equal to H delta H minus T delta S at a constant temperature and constant pressure. Now I have again plotted G of solid, G of liquid, that is a crossover here, you can see here. So now consider temperature, any temperature, this temperature suppose, this white dotted line shown here, this is a temperature selected T1. At the temperature, delta G is nothing but this difference shown by arrow. Delta G is the G of L minus G of S. Okay, so these are all shown you here. At temperature T2, this is what is the difference, the arrow, small arrow, so arrow has got reduced, numerical value of arrow. And at the melting temperature, or the certificate, this is Tm, this is vanished, there is no delta G, that is equal to 0 basically. Now if I go to the other side, what is happening? I put arrow in the downward sign, there is a reason behind it, it will come very clear to you now. So you can see clearly as you go away from the melting temperature on the right side, again delta G is increasing, but the sign is changing. Okay, so this is where the G is equal to GL at the melting temperature. Below the melting temperature, delta G, remember delta G is GL minus GS, this thing you should not forget. That's why it is written delta G superscript L to S, solid water, liquid water to solid ice. It is equal to less than 0. Am I clear? It is very clear, because you can see here the GL is higher than the GS, right? Yes. Okay. Now let us see on the right side. On the right side, delta G is basically equal to positive. Okay. Why it is showing positive, negative, or am I doing some mistake? Okay, let us correct it. Okay, I mean everybody can have mistakes. So the way delta G is defined is between product minus parent phase. So that means GS minus GL it will be. I have written wrong, so you can correct it in the actual. So this is GS minus GL. So if that is the case, then delta G below Tm, temperature less than Tm is less than or equal to 0, or less than 0 actually, and above the melting temperature or above Tm it is greater than or equal to 0. That is clear, because this is GS is higher here than GL, so therefore it is greater than or equal to 0. GS is lower here than the GL, so therefore less than or equal to 0, and at the melting temperature this is equal. So this is how we can calculate. Okay, let us explain in detailed manner this one. So what you can understand from this very clearly, that above the melting temperature, because delta G is 0, therefore solid will never be stable. Correct? There is no driving force available for the liquid to transform into solid. On the other hand, below the melting temperature, it is less than or equal to less than 0. That means you have a finite force available, finite energy available to it. So what is the meaning of negative and positive? Let me explain in thermodynamics terms of you. That is what probably you have already seen. Negative change of any function, especially G in thermodynamics, means you have available energy to you. System has energy available to it. Positive means system has no energy available to it. This is the convention we use in thermodynamics. So that means that below the melting temperature there is a driving force available, net energy available for the system to transform to solid. On the other hand, above the melting temperature, above the Tm, there is no energy available for the system to transform the liquid to solid. Okay. So, this sign of delta G tells you the direction of transformations. At the melting temperature, that is what is shown as dG, or you can write down delta G is equal to 0. So, therefore, at the melting temperature there is no change of positive and negative change of free energy, this is vanishing, and because of this vanishing free energy change there will be no energy available for the system for transformation. The system will not undergo any transformation. That is what happens at 0 degree Celsius temperature and 1 atmospheric pressure. Ice and water will coexist, they will never transform to each other. On the other hand, below the melting temperature there is a negative sign of delta G. Delta G is less than 0. A negative sign means there is a driving force available for the system to transform. But above the melting temperature it is greater than 0. That means there is no driving force available for the system to transform from liquid to solid. In a nutshell, we should not spend more time on that. In a nutshell, the sign of delta G tells you the direction of transformation. If for a particular reaction, suppose A plus B going to C, if the sign of delta G is negative in this direction, A to B, A plus B going to C, that means reaction will happen. If on the other hand the sign of delta G is positive, the reaction will not happen. This plot is telling you that answer. In a simple ice water analogy, I am giving you this concept that sign of delta G is going to dictate the direction of phase transformation. Finally, the answer of phase transformation direction, whether solid will transform to liquid or liquid transform to solid, can be obtained by simply calculating the delta G and plotting in this manner. Okay, so now that is for very easy things can be done for the pure systems. What will happen if we have an unpure system like alloy or mixture of two phases or two components like water with salt, coffee with sugar. Okay, when you have two components mixed together, can I use the same analogy? Answer is no. So this is what we are going to discuss in the next lecture, whether can we calculate G and delta G of those systems and get the similar answer. Remember, the conditions will remaining same. The conditions of phase transformation directions will remain same. Things which are going to change is how do you calculate the G, H and S parameters for those systems. Okay, that we will discuss in the next class.